Actually, let's look at what the Voronoi regions look like. So halfway between, this is at -8 and this is at +6. So what's the halfway line between these two guys? Should be at -1, right? Similarly, between these two guys, this guy's at -6 and that's at +8, so that should be at +1. Actually, let's focus on this guy first. So halfway between +7 and -7 is obviously 0. Halfway between halfway between this guy and this guy is at 0. Halfway between this guy and this guy, so this is at -6, -7. This guy's at +6, +7. So if I connect those, it should go through the origin, and halfway between them should look like this. So in fact, the Voronoi region is the union, or excuse me, the intersection of all of those Voronoi regions. So I get this. Okay, so there's that's halfway between these two guys. So all the Voronoi regions agree on this boundary, and then I get this. So I get this kind of notched Voronoi region. Let's see. Yeah, I think if you followed all these arguments out, you would get Voronoi regions that look kind of like, actually, anyway, this is enough to make my point. So, Voronoi region for this guy looks like this. That's not a rectangle, so we can't use the analysis that we used before. And you can see why. If I went to a larger number of users, for one thing, we probably couldn't write it down. We'd probably need a computer to solve it. And secondly, as these Voronoi regions become more and more complex, it becomes harder and harder to search. It becomes harder and harder to locate where exactly points are with respect to all the boundaries. So as the number of boundaries grows, you have to check all the boundaries. So before, when we had just these nice straight line segments, it was easy to figure out on which side you were. But now that we have these sort of faceted regions, it's much harder. So it turns out that if you have a large number of users, the complexity of of doing this optimal detection, it turns out to be NP hard. So it's been shown that this problem of trying to locate all these points within all these Voronoi regions for an arbitrary number of non-orthogonal points is NP hard. This version of optimally trying to determine where all the points are is called multi-user detection. And as you can see, it is possible, but it's really, really hard. Okay, now let's say we were only interested in user 1. So in that case, what could we do? We could map, one thing we could do is we could just say, okay, user 1's bit, if user 1 sent a 0, those are my bits, and if user 1 sent a 1, excuse me, backwards. If user 1 sends a 0, it's one of these 2 points. User 1 sends a 1, it's one of these 2 points. So in other words, why not put the dividing line there, and then if I don't care about the y direction, I can collapse that, and then basically I'm distinguishing between either these points or these points. So the worst case scenario is that I have the inner 2 points, which I can still distinguish. And what I'm doing is I'm ignoring the effect of the other user. So what we can do, it turns out, is we can pretend that this variance, or this this sort of jiggling in where exactly on the x-axis user one's transmission is located, we can pretend that that's noise. So that's the other approach. So what we're going to do is basically this. We're going to say the signal I transmit is user 1's bit, that's S1, plus user 2's bit, times S2. But I'm only interested in what user 1 is sending. So let's boil that down to what we had before. Let's normalize user 1, and then we get 1 over root 7nc v1 sx plus, and this I don't really care about, so I'm going to call this a vector of interference. Let's call that I vector. So what do I do at the detector? At the detector, what I observe is y, which is this, the signal I'm interested in, plus the interference, plus some noise. So what do? I pass this through my filter. What the filter does is it basically takes y and takes the dot product with sx. So what I end up picking off, again, is v1 sx dot sx is 1 plus interference dot sx plus the noise dot sx. This is what we used to deal with. We're very accustomed to dealing with that. Up till now, we've assumed that these cross terms were all 0. But now, they're not. So what is this? In the 2 user case, all this is v2 s2 dot s1 dot sx, which is equal to v2 times 1 over root 7nc s2 dot s1. So the intensity, let's now note 2 things. Firstly, we established a second ago that this is non-zero. For another thing, it's going to be random because b is either plus or minus 1. For another further thing, these signals are not going to line up quite as neatly as this, so there could be some asynchrony there. But in any case, this quantity appears again. And what this quantity is, again, is the cross correlation. So what we're going to do next time is basically we're going to group together all of this as noise. And in order to do that, this is a random variable. So what I have here, it could be shown that this is 0 mean because b is either plus or minus 1. This is also 0 mean noise. So basically what I need is I need the variance of this. So for the noise, I have variance. For this thing that I'm going to treat as noise, I'm going to get the variance of this, and that, it turns out, is going to be proportional to this cross correlation. So the cross correlation comes up over here because that's what's skewing this box. And the cross correlation comes up over here because that's the noise that I'm trying to ignore. Okay, any questions? All right, we'll see you on Tuesday.